Hi there, Turgeon here, bringing you physics from afar. This is Mr. Grady's presentation, and it is based upon the Turgeon presentations, but in his own style. Topic we could call wave interference. This goes back to one of those key questions, one of those big questions, which has to do with how do waves interact. And you can talk about how waves interact with each other, and you can also talk about how waves interact with their surroundings or with boundaries or with the medium itself. In this case, we're focusing on waves interacting with each other. Have you ever been in a wave pool? And in particular, when the wave pool is in that setting where it's actually producing two waves that are at different frequencies. Hey, quiet out there. And the two waves are interfering, so you can go to one spot where there's not very much oscillation. You can go to another spot where you're bobbing up and down furiously, and that's really fun. So we have two different kinds of wave interference. You can have two waves that are approaching each other, and they're both positive amplitudes. And you can have two waves coming at each other, and they're negative amplitudes. And we're going to talk about what results from that and the names for each of those. And we're going to have energy considerations. So picture this is just like a basic spring, but we draw these waves as squares really only for the for like test and quiz taking exercises, so that they're easier to draw the result. So when these two interact, when they overlap, you can imagine that there are arrows indicate. You can imagine that this is two waves that are traveling along a spring. So this is not just some kind of static situation. These are coming at each other. I'm drawing with a mouse, so forgive my janky arrows. So these are coming at each other. They're gonna interact very, very briefly, as you may have seen with the various springs and slinkies and stuff. And when they do overlap, it's going to produce a wave where the amplitude gets larger very, very momentarily. And make a little note in the margin. It's only the amplitude that gets larger. It's not the wavelength. If you look at what I attempted to draw here, I kind of wanted to make it look like these were the same wavelength. But clearly there's a brief moment of overlap where you have suddenly a really large amplitude. That's called constructive interference. And then of course you can have situations where two waves come at each other. I deliberately drew these with different wavelengths. These waves will interact and they will actually briefly cancel out. So you're going to have just like a straight line medium. There's just kind of nothing there. This is called destructive interference. Of course, I'm just talking through this and you can just pause the video and write down what you need to. A lot of people just reflectively say deconstructive. People often say deconstructive interference. It's destructive interference. The waves combine to produce a smaller amplitude. Again, not a different wavelength. In this case, you can't even see, but the wavelength is the same. In the case of sounds, in the case of ocean waves, that means you're like thrown to a greater height if you're riding along. And in the case of sound, it would mean you'd hear actually softer or louder sounds, which there are equivalent phenomena like that we could talk about later. When the waves interact in a particular way at under the right conditions, with the right material, at the proper frequency, you can get a standing wave. What happens is a wave moves along a spring or a string or even the air inside a tube, and the wave gets reflected back. When the wave gets reflected back, it produces destructive interference at points that we call the nodes, and it produces constructive interference at places we call antinodes. And you end up with a standing wave like you've seen in class, where it's I'm going to try to draw this with the mouse, and we will see how much I flounder on a humid day with the mouse trying to stick to the desk, drawing a standing wave, and I'm going to cheat a little bit. So the wave at one brief moment in time looks exactly like that. And then a half a cycle later, the wave looks like that. And these produce what I like to call football shapes, because each of these shapes inside looks kind of like a football. It's not exactly a circle. Okay, so this wave is oscillating between these two conditions, and that's what we call a standing wave. This is the point called a node. Here's a node. Here's another node. Here's another node. And these are the points called the antinodes. This has 3 antinodes where we have constructive interference. So to sum it up, constructive and destructive interference are when two different waves interact at the same point in space, and they produce a different amplitude. That means that at that moment you have a temporary increase or decrease in the energy at that point in space. This has been Turgeon, bringing you physics from afar.